Hello everyone, welcome to lecture 53. We are almost at the end of our course, right. So in the previous class we were actually looking at what these Kramers-Kronig relations are, so how a response function as a function of frequency, right. So it depends on frequency, has an imaginary part, has a real part, and how the real part is related to the imaginary part. This is necessary, relating the real part to the imaginary part through what is called a causal transform or a Hilbert transform is necessary to maintain causality, right. So if these are not related, then causality breaks. Okay. What this mathematical fact of causality also tells us, so the causal transform, the mathematical transform which is a causal transform also tells us is that to maintain causality, the property that looks dissipative, which is the imaginary part of susceptibility, let us say, which is resistance, right. So in its frequency, in its spectrum, right. So in its frequency spectrum also has information about the real part, which is susceptibility, the real part of susceptibility, which is capacitance, right. So the energy conserving properties are related to energy dissipative properties, not in a straightforward way, but through the spectrum, right. So in frequency space, right. So phi of omega, phi I of omega will be related to phi r of omega as a Hilbert transform, right. So all the frequencies, not just the omega frequency, but all the frequencies from 0 to infinity matter to determine phi I of omega from phi r, right. So the phi r of omega. Okay. So that is what we did, and we stopped at a point where we said phi r is actually, so let me change the color. So phi r actually talks about fluctuations in order parameter, or it is also scattering in terms of, if I look at it in terms of refractive index, this is the real part of refractive index, or it tells us what is scattering. Phi I tells me about absorption, or phi I tells me about dissipation, right. So from a refractive index point of view, this is absorption, and so we are saying that the fluctuations in statistical mechanics, the order parameter, right. So we looked at all the conservative properties being fluctuations in order parameter, they are related to each other, right. So that is the crux of what is called fluctuation and dissipation theorem. We just looked at a form of it which is called Kramers-Kronig relations. Okay. So we are not going into more details about fluctuation dissipation relations and theorem, but so this is where we will halt that discussion. Okay. So let us actually try to understand what this formula is. So in some sense I told you that if I have Ni of omega is just minus infinity to infinity Nr of omega divided by nu minus omega d nu, right. So this is the Hilbert transform or the causal transform, right. And from here we change the integration limits from 0 to infinity, and then we made a different formula, right. So but let us start with this formula, right. So let us try to understand so how this looks like. So if I have Nr of omega, right, so I give you Nr of omega which does not have any dispersion, right. So this is Nr as a function of omega, right. So even so I am going to assume that the same is the case even in negative omega, right. So Nr of omega is a constant with some interpretation of what negative omega is. I am going to say Nr is a constant, it is constant throughout the frequency domain. Okay. So if Nr of omega is constant, I want you to calculate what Ni of omega is, right. So Ni of omega is minus infinity to infinity Nr. So Nr of omega is constant, that is just Nr 1 by nu minus omega d omega, d nu, right. Now that is so I can just make a change of variable. So nu minus omega is my nu x, right. So then I have Ni of omega is equal to Nr integral minus infinity to infinity 1 by x dx, right. So d nu is equal to d nu minus omega, right. So that is my transformation, that is equal to dx. Okay. So now the question is, what is 1 by x dx, integral 1 by x dx, right. So now 1 by x, so it feels like integral of 1 by x dx, since 1 by x, so from minus infinity to infinity, since 1 by x is a odd function, this should be equal to 0. It feels like that, right, but we have an issue, right. So for example 1 by x, right, so is as x tends to minus infinity it is 0, but as x tends to 0 it goes like this, right. So this is my 1 by x, and on this axis there is a sudden discontinuity at x equal to 0, right. So there is a discontinuity at x equal to 0, this is 1 by x as a function of x, okay. So 1 by x as a function of x has a discontinuity at x equal to 0, but it feels like if I integrate it from minus infinity to infinity, right. So the area under this curve and the area under this curve should sort of cancel out each other and it should become 0, right. Now how do we integrate such things? So we say, okay, so integral minus infinity to infinity 1 by x dx is equal to integral minus infinity to something like epsilon 1, or so I am going to say infinity to 0 1 by x dx plus integral 0 to infinity 1 by x dx. To get rid of this discontinuity I go towards 0 from here and I go towards 0 from this side, right. So essentially that is I use two limits, right. So one of them being a limit b or b1 that tends to infinity, right, or minus infinity, and epsilon 1 that actually tends to 0, right. So from negative, okay, plus integral epsilon 2 that tends to 0 but from the positive side to b2 that tends to infinity from the positive infinity 1 by x dx, right, and that is equal to log of epsilon 1 by b1 plus b by epsilon 2. So b2 by epsilon 2, okay. Now depending on the choice of b1 and b2, epsilon 1 b2 epsilon 2, this integral can take several values. Right. However, so we say that is why we use the word principal value. For principal value I am going to tend this to 0 the same way as I tend epsilon 1 goes to 0 the same way as epsilon 2 goes to 0, or in other words epsilon 1 will be equal to epsilon 2 and b1 equal to b2, and in that case so the principal value of this integral 1 by x dx is actually equal to 0, right, and our this is called Cauchy's principal value, okay. So there is more mathematics to it, but this is a very simple and fast explanation of what principal value is, right. So the principal value actually goes to 0 in this case, and that is indeed so when I do Hilbert transform I am actually writing ni of omega is equal to minus infinity to infinity n r of omega divided by nu minus omega d so d nu, right, but the principal value of this is what I am taking. I am not taking any value, right. So that is what this p means. P is p means I am just taking the principal value of this integral, okay. So the principal value is 0, that is good, which means if I do not have a frequency dispersion, right. So if nr is constant there is no frequency dispersion in real part of the property, then there is no absorption. Or dissipation, okay. So what are dissipation less systems? If I ask you this question, what is a system that is dissipation less throughout its frequency spectrum, then I can answer this question by asking so this material does not absorb anything. Let me give you that material. So how do you prove it to me? You prove it to me that so you can look at nr, which is the real part of refractive index as a function of frequency, and then show that this does not have any dispersion, right. So, in actually it should be from 0 to infinity or minus infinity to infinity, there should be no dispersion of NR, only then will there be no dissipation, no absorption, right. But that is not true, right. So, we we always have all these resonance phenomena where NR or resonance and relaxation phenomena where NR is actually changing, NR or epsilon r, right. So, with the okay, so let's write epsilon r, right. So, we always have this resonance and relaxation phenomena where so there is a frequency dispersion, there is always a frequency dispersion. And so there is always dissipation or absorption, right, except in vacuum, right. So, in vacuum NR versus omega will be like this, right. So, in vacuum there is no dissipation. But it should be perfect vacuum, right. So, creating perfect vacuum is another thing, but in vacuum there is going to be no dissipation of light, but in general or no absorption of light or dissipation of electromagnetic energy, but in general so there is always some sort of these dissipative factors, okay. So, you can actually yeah. So, but so what you can say however is if I look at this frequency range, right. So, in this frequency range it looks like NR is a constant. So, the absorption will be minimal, right. So, absorption here or absorption is typically called K or we used it as epsilon I will be or Ni sorry will be minimal, right. So, in that region absorption will be minimal. I mean it is there, it is not 0, but it is still minimal, especially if your frequency spectrum is flat, okay. So, in to get these properties ideally you should measure these properties as a function of frequency, and so the frequency spectrum should range from 0 to infinity, and in that case so if I do not have any resonances relaxations in some medium, then I say that there is no absorption, and then NR is a constant, then the real part so then the imaginary part will be 0, right. That is what we just proved, okay. So, we will come back to this. So, the point that I want to make is to measure or to estimate phi I from phi r, ideally one would want phi r as a function of frequency omega, where omega goes from 0 to infinity, right. So, 0 to very large frequencies. So, I have to measure it throughout the frequency spectrum, and only then can I use my Hilbert transform and accurately predict what phi I is. Any other sort, if I just measure it in a limited frequency range and say NR is constant and absorption is so I cannot be very sure that absorption is 0 because my integration limits have now changed, okay. So, then absorption limits so absorption could be close to 0, but not exactly 0, okay. So, that is some caveat that one needs to remember, okay. So, that is the first thing. Then the second thing is I want you to do an exercise where you take some phi r which changes with frequency as phi r relaxes with frequency, some function which goes like this, right. So, we have the form of this function, right. So, you can look at what is how polarization or how chi relaxes with omega, right. So, we derived that, and if phi r is this function phi r of omega, then I want you to show that phi I of omega is actually going to be as we have drawn, right. So, we will have a peak here, right. So, you can try to show it to yourself numerically, or at least try to argue out that this is going to be the nature of phi I of omega, okay. Similarly, if phi r of omega is some sort of a resonance, right. So, which means it goes up, there is a resonance peak and there is an anti-resonance peak, this is phi r as a function of omega, then phi I as a function of omega is going to be peaking here and it is going to come like this, okay. So, and then you can just show these two phi I of omega has this shape, has the shape as shown above, given phi r of omega at resonance, right. So, both at resonance, both for resonance phenomena as well as for relaxation phenomena, phi I of omega is going to peak, right. So, it is going to show a peak, or it is going to show maximum dissipation at either the relaxation frequency omega naught or the resonance frequency omega naught. Okay. So, depending on the phenomena, phi I will show a similar behavior, it is going to show a peak and then go down. Okay. So, that is something that you can show just by integrating the Hilbert transform, right. So, you can use the integral forms as we have shown earlier. Okay. Now, comes the issue of how do we measure dispersion? Dispersion meaning frequency, dispersion, let me write it as dispersion, meaning the change of property or the property as a function of frequency, right. Any property should ideally be measured as a function of frequency, then and only then do I know the complete information about the property. So, let me make that point. For us to know the complete information about any property, it needs to be measured as a function of frequency. See, right? Now, what I can do is I can measure the real part of the property, let us just call that refractive index, because so we are as a function of omega, right. So, or phi r as a function of omega, okay. Or I can measure phi I as a function of omega, right. Now, if I measure phi r as a function of omega, I am going to call these as scattering experiments, because this is the scattering part of refractive index is what I am measuring, right. So, these are called scattering experiments. Okay. If I am measuring the dissipation as a function of omega, so these are what are called spectroscopic experiments. Actually, both of them are spectroscopy, but these are what are called absorption or emission experiments, right. So, both these things, so the frequency dispersion, if I get the frequency dispersion, both these things together come under the purview of what is called spectroscopy. Spectroscopy means you change omega and then you measure the property as a function of omega, that is it, right. So, it is a very simple definition of what spectroscopy is, but it tells you a lot about what are the dynamics in the material that give rise to these properties, right. If I do a spectroscopy measurement, so I understand a lot about the dynamics of what is happening, right. So, at different frequencies, okay. And spectra means a frequency spectrum, right. So, in a certain range of frequency I do measurement of my property, okay. So, I can either do scattering based spectroscopy or I can do absorption or emission based spectroscopy to get complete, to get information about either phi I or phi r, right. Now, if I have phi r as a function of omega, I do not necessarily need to do phi I as a function of omega, because these two are related to each other. Phi I as a function of omega, these are related, right. But this omega should be the complete omega 0 to infinity, right. So, if I am really going to high frequencies, I should do these experiments at X-ray frequencies also. At the same time, I should do these experiments at DC frequencies, which is very small, right. So, that is the range that I am going to scan, right. So, for example, so DC or 10 hertz is some sort of measurement that I do in lab, electrical measurements that I do in lab, where electric field is oscillating at 10 hertz, right. So, let us go to our stimulus being electric field, right. At the end of the day, every stimulus, right. So, as you keep on increasing frequency becomes electromagnetic in nature, right. So, be it mechanical, be it so mechanics interacts with the the dipoles in the crystal, and then that becomes electromagnetic in nature, and so on and so forth. So one can think of all the stimuli being electromagnetic in some sense, right. So it's a deeper statement than what I have just mentioned, but so any sort of oscillating stimulus will be related to some kind of electromagnetic response, right, that is generated. Okay. So I can apply this frequency at 10 hertz or 10 power 15 hertz, that is the visible light, right, or 10 megahertz, right, or 10 gigahertz, or so gigahertz, which is the microwave frequencies, or so somewhere here are what are called radio wave frequencies, right. So these are microwave frequencies. Okay. Or I can apply so the stimulus at something like terahertz, right. So now terahertz is tricky, right. I will tell you why. Or I can apply this at infrared, this is visible, and then I have UV, right. So UV goes up to 10 power 16, 10 power 15 to 10 power 6, this is 10 power 14, this is 10 power 15 to 10 power 16 hertz. Then I can do X-rays, X-rays can go from soft to hard, right. Hard X-rays are 10 power 19 hertz, right. So let us stop there, right. So beyond X-rays I do not get anything with respect to the electronic properties of materials, I get nuclear properties and things like that, right. So this is the complete frequency range. I am scanning from 1 hertz, which is 10 power 0 hertz, all the way up to 10 power 19 hertz. I can even go slower than 1 hertz, right. So there is some 20 orders of magnitude of frequencies that I have to scan, right. And you will see that spectroscopic techniques, so they work in certain frequency ranges, right. So all these so all these techniques that scan across these 20 orders of magnitude of frequency and give you information about the scattering property or the absorption property are called spectroscopic techniques. However, no single spectroscopic technique can scan all the 20 orders of magnitude or 20 orders of frequency dispersion. Okay. So we do different sorts of spectroscopy in the low frequency range, in this frequency range it is different, this frequency range it is different, and so on and so forth, and they all have different names. Okay. So that is exactly what we are going to study from now on. Okay. All right. So now before going into the details of what spectroscopy does and what spectroscopic techniques are, let us actually look at again let us come back to absorption and scattering. Right, from a quantum mechanical perspective. So what did I say? I said absorption means I equal to I naught e power minus alpha x, right. In other words, this is absorption of energy, right. So which means this is absorption of energy, which means if I send in light of some frequency h nu, so there are some photons. So if I have absorption at a frequency nu, it means if I send n photons of frequency nu naught, the material will absorb n1 photons at that frequency. Okay. And I am detecting n minus n1 photons, right. So, in some sense if I am n photons are coming in, then n 2 photons are coming out. So, the material has absorbed n minus n 2 photons, right. So, okay. So, the material has absorbed n 1 photons. Okay. Every photon has the same frequency omega naught, let us say, to start with. Okay. So, that is absorption. Now, what is happening to the material when the photons are being absorbed, right? What happens to the material? Right. So, from now on there should be transfer of energy from photon to something else, right. So, there is going to be transfer of energy from photon to the material, right. Now, we said okay, this transfer of energy can be heat, it gets dissipated as heat, there is T s dot and all these things mean the same, right. So, but what is heat, right. So, how is the material heating up? You are dumping energy into the phonon modes of the material and these phonon modes are vibrating. So, photon in some sense, if I am just looking at it as a particle picture, a photon is giving off its energy to phonons or some other particles, right, which are in the material, right. So, that corresponds to absorbing this energy and dissipating it in the form of heat or whatever is the other forms of energy, but the material is absorbing energy, electromagnetic energy. Okay. Now, now how can a material absorb energy? So, if I shine so very quantum mechanically, let us say there are electrons, right. So, these are electrons or phonons, it does not matter, right. So, there are some particles, electrons have a couple of energy levels, this is energy level E1 and this is energy level E2, right. Now, if I shine light of energy h nu, right, now and h nu happens to be h nu happens to be delta E, right. So, then the electron can get excited, right. So, by absorbing light, electron gets excited to a real state E2 from E1 such that E2 minus E1 equal to delta E, right. So, so this thing, right. So, if there is a real state to which an electron can get excited to, because there are so many energy levels in a material, right. So, if this is a real state to which electrons can get excited to, then so this absorption is real, right. So, there is a real absorption, the material is taking away the energy from the photon, right. So, that means the material is taking away and getting excited. What is the material doing? It is the material is getting to an excited state, takes away energy from from photon and is getting excited, which means it is no longer in ground state. This electron is in a higher energy state, it is no longer in the ground state, right. And exciting the material costs energy, exciting the material to real energy states, this costs energy which comes from the photon, costs energy, and that energy comes from photon, right. So, this is absorption or this is the dissipation, right. So, later on it de-excites and tries to dissipate its energy, that is a different ball game altogether. Okay. So, so first absorption happens, right. So, the material, if there is a real state to which this material can get excited, and what do I mean by material getting excited? There are material is made up of so many electrons, phonons, etc. Everything has its own energy states. If there are real energy states to which these particles can get excited to, then that is an excited state of the material, right. And so if I am really exciting the material, and to excite this material I take energy from the incident photon, right. So, incident photon that I am shining on this material, right. And so it gets excited to a real state, and that is the process of absorption if I am thinking of it quantum mechanically, right. So, I am just absorbing light at a frequency omega, right, which means I am absorbing energy, right. So, my electron or my phonon or whatever is the particle, right. So, spinon, magnon, whatever, right, is absorbing energy from light and then getting to an excited state. Okay. Okay, so that is absorption. Now, what is scattering? Alright, so now I have an energy state E1, let us say, I mean this is, it can be so I will tell you what these energy states are when we actually go into details of frequencies. If I have an energy state E1 and so I want to excite and let us say this there is some sort of a band gap here, right. So, there is this is valence, this is some conduction band is some band is here, right. So, but this is a band gap. Okay. So, now so I shine light into my material, but that light has only an energy delta E is only this, but this is there is no real state, no real energy state here. Or the density of states, in other words, right, at E1 plus delta E equal to 0, right. So, I do not have any density of states. So, by definition there cannot be any electron there or there cannot be any photon any phonon in that state, right. But still I am supplying an energy delta E to the material. So, what does the material do now? Material cannot absorb because the system cannot get excited to this state, the electron cannot get excited to this state, right, but the electron can change its momentum and do other things, right. So, this sort of a thing, right, so where the electron cannot really go there, right, so but you sort of interpret it as if the electron goes there and comes back without any change in energy, right. So, or so this creates some sort of change in the k vector or change in momentum of the electron really, but not really the absorption. So, there is no change in frequency of this electron or there is no change in energy of this electron, right. So, such a state is called virtual state. It is not real, there is no real absorption, right. It is just some sort of virtual absorption which is equivalent to scattering, right. It is like my imaginary part. Imaginary part, in general real part is something that I am interested in, right, but imaginary part I am making it mathematically convenient to interpret it as something else, right. So, similarly here there is a virtual state, it is not a real state, and electron you think of electron getting excited to the virtual state in almost time t equal to 0, right. So, in so there is no time spent for the electron to get excited to virtual state and get de-excited, right, no energy cost at all, 0 energy, right. So, but if there is a real state there, if there is some density of states, then a electron goes there, spends some time and then decays, right. So, there is some time for this for this excited state, but if there is no real state, if it is a virtual state, you can imagine that there is still an excitation and a de-excitation at t equal to 0 at so instantaneous, right. So, electron does not spend any time at the excited state, thus the material it is not going to take any energy from the material, right. So, there is no energy dissipation or the photon is not giving off any energy, okay, because there is no state for the electron to go and spend some time. Electron should spend some time in that state for it to lose energy, right, but there is no state for electron to go there and spend time. As a result, this is what is called virtual state, and virtual states are important for scattering, right. So, electron still did something, right. So, it's there is still some sort of you have set in some sort of an oscillation, right. So, or some sort of change in momentum of this electron or so this is important for scattering, right. So, virtual states, no absorption has happened, but virtual states are important to explain scattering, and by scattering we also mean the real parts of thermodynamic properties. Okay. Let us start with a very simple example, right. So, okay. So, I have a material which is a metal. this is metal, right. If I have a material which is a metal where this is the Fermi level, right. So, this means what does it mean that it is a Fermi level? So, I inject electrons, right. So, this is a metal, I have a metal here, or I have an electrode, right. So, this is called an electrode, sorry. So, I inject, so this is my material with with a conduction band which is just half filled, right. So, this is metallic, this is half filled conduction band, right. Now, this is an electrode and this is another electrode. I inject electrons from this electrode, this is the inject electrons from the electrode into the material. And I collect electrons here. This is any transport measurement, right. So, I am injecting electron to the through the electrode and I am collecting electrons here. Okay. So, this is a typical transport measurement. Okay, and then I drive in a current and I measure what that current is. Okay, so that's the transport measurement, but very at an electronic scale you think of it as injecting electrons and then collecting them here. Now, where are you injecting electrons? So, I am injecting an electron, I apply an electric field. So, this electron has needs to be injected, right. So, but where can I inject an electron to? An electron can be injected only to a level that is free, I mean so that does not have any other electrons, right. So, all the levels, if I am doing this measurement at 0 Kelvin, all the levels until here, right. So, these are, although this looks like a band, there are so many individual levels, right. So many, so much packed individual levels, right. So there are huge number of levels, some 6.023 times 10 power 23 number of these energy states, and all of them are so closely packed that I see a band, right. So, which means even above that I have levels, but all these levels, all these energy levels are unoccupied, right. Now, if I am injecting an electron, what is the so can I inject an electron to just I cannot inject electron below the Fermi level, because all these already have electrons, right. I should be able to inject the electron just above the Fermi level, correct. So, just above the Fermi level, is there a state? So, then I ask the question, is there a state just above the Fermi level to which my electron can be injected or excited, right. So, it does not matter whether I inject electron or I just excite electrons from here, it does not matter. Okay. Now, is there a state? In this case it looks like there is. Okay. But then I am going to ask a question in the next class, we will come back to this, right. So, how much above the Fermi level? Is it 1 nano electron volt? Is it 1 pico electron volt? What is it? What is the minimum energy above the Fermi level? There can be a state, right. And so that is the question that we are going to ask in the next class. But let us say for now it looks like there are so many states that I can inject an electron to one of these real states, right. Now, if I am injecting an electron to one of these real states, what I end up measuring is a dissipative property. If I inject and excite an electron, right. So, to an empty state, but this empty state is real now, right. So, excited to a real state, right. In this spectroscopic technique, I am going to measure the dissipative property, and you will already guess that through transport measurements we measure a dissipative property which is conductivity, conductance or conductivity. Okay. We will come back to this in the next class, but let us end this class by looking at another example where I do not have a real state. So, essentially I have a conduction band which is empty. I am looking at case of a semiconductor, and I have a valence band which is full, this is filled, this is empty. Okay. Now, so and the Fermi level is here, right. The question that I am asking is, can I excite an electron right. So, from here to some empty state that is above the Fermi level at 0 Kelvin, or can I inject an electron into some so close enough to the Fermi level, right. So, the question that I am asking is, can I inject an electron close to the Fermi level at 0 Kelvin. Okay. So, I have a metal, and metal has this as the Fermi level, right. So, the Fermi levels match, but through the metal is a reservoir of electrons. Can I inject an electron close enough to the Fermi level? Turns out that the density of states here is 0. Okay. So, there are no real states close to the Fermi level, right. So, the excitations are just going to be virtual. So, as a result, I am going to measure properties that are more like scattering properties and not absorption properties, right. So, in this setup, right, if I do some spectroscopy and the scattering property that I end up measuring through such transport measurements, right, turns out to be susceptible dielectric constant, or right. So, we will exactly see how to how that works in the next class, but or susceptibility, or real part of dielectric constant, or susceptibility, okay, or capacitance, right. I end up measuring the capacitance if I force an electron to get excited to some level which is just a virtual level, right. So, I am forcing electrons to get excited virtual levels. Now, what is this virtual level, at what frequency is it away from the valence band, all these things we will see in the next class, right. So, then I will measure a scattering property, and in this case the scattering property is just dielectric constant or capacitance. Okay. So, let us actually look at that, right. So, what is this frequency? So, you can go back and see at what frequencies do we measure capacitance, right. So, let us ask an experimental question. Does one measure capacitance in a lab, right. So, in a typical impedance LCR meter or impedance spectroscopy. So, it turns out that these are frequencies which are less than 10 megahertz, right. So, 1 hertz to a few hertz to 10 megahertz. Okay. So, what do these frequencies correspond to in energy levels, and so what is the excitation of these electrons going to be? That is the question that we are going to start in the next class with. Okay. So, we will start our discussion in the next class with the first kind of spectroscopy called impedance spectroscopy, right. And impedance spectroscopy, the properties we end up measuring are epsilon r and epsilon I. Epsilon r is related to the capacitance, or the real part of dielectric constant. This is capacitance and this is conductance. Okay. This is conservative, this is dissipative. We already saw how small signal measurements work, and the way we are doing small signal measurements, you can bunch it and then call that as impedance spectroscopy in some sense. Okay. So, we will see how this works in the next class, and until then I take your leave. Thank you very much. I will see you again in the next class. Okay, I am done.
1 minute, sir. At the end portion, can you do it 1 more?
Yeah.
Not writing, sir. Only the.
Yeah. So, in the next class we will actually start with impedance spectroscopy, where we look at capacitance. I mean, so we have already seen something like small signal measurements. that can be bunched into these measurements called impedance spectroscopy, and we will see how this works from this quantum mechanical energy picture, right. So, what is the frequency that we give, what is the energy that we give to electrons, and what levels do they get excited to, what is the capacitance part of it, what is the conductance part of it, what is the fluctuation part of it, what is the dissipation part of it, everything coming from one spectroscopy experiment. Okay. So, we will start with impedance spectroscopy and then move on in the frequency range. Alright, so I will see you again in the next class. Thank you very much.